So this is one of 3 sets of atomic structure questions, all multiple choice, all past paper A-level AQA chemistry questions. I'm going to recommend that you have a look at the question, pause it, and then when you've tried it, you can go through and check how you have done and work out if there's anything that you need to look into a little bit further. So let's start with question 1. So we have got here the idea that He plus 2 particles are being fired at a thin gold sheet, and we're seeing that most of them pass through to P. Now it's important to point out that in this case, every single one of the answers is true. A, B, C and D all are valid. Gold does contain electrons, protons and neutrons, and gold atoms are mainly empty space. But what this experiment actually tells us and proves to us is that gold atoms are mainly empty space, because those He2 plus particles are not being prevented from carrying on directly forward to point P. So this is a factual recall question about time of flight mass spectrometry. Let's go through the answers, take a look at them, see if we can establish why some of them are incorrect, and then by virtue of that we can see which one is correct. Taking a look at B to begin, it's the wrong way around. You don't form positive ions by gaining electrons, you do it by losing them. Particles are detected in order of their kinetic energies is false. If you remember, when we accelerate the particles, we accelerate so that they have the same kinetic energy. It's just that small particles then move faster. And ions are not accelerated by a magnetic field, they are accelerated by an electric field. Now that leaves us with A, which you possibly knew straight away was correct. This is how we actually determine abundance. We measure the total current as a result of each isotope, and that current is proportional to the abundance of that ion. So on this question, you will almost certainly be working in tandem with the periodic table. I would recommend you have that as part of the process. Don't just try to remember the numbers, because you've got lots to remember as it is. So we have got a K plus ion with a mass number of 41. So let's work out what we can do to try to lower the odds of a wrong answer and increase the odds of a correct answer. Well, we know because its atomic number is 19 from the periodic table that it's going to be A or C. We're now down to a 50-50 before we even move on to consider the remaining data. Now, what else do we know? It's K plus. So because it's a K plus ion, that means it's lost 1 electron. So my 19 protons and my 18 electrons will give me the K plus ion. And I could have worked out the 22 going from 19 to 41, but actually I didn't need to do that. Once again, handy to use the periodic table on this rather than try to remember the data. We're dealing with an Fe plus 2 ion, and it has a mass number of 57. So if I take a look at the actual periodic table data, we know that iron has an atomic number of 26, which means it has 26 protons. Now, to become a plus 2 ion, we have lost 2 electrons. We know that in an atom, number of protons is equal to number of electrons. So 26 take away 2 gives us 24 electrons. We're now down to 50-50. Our answer is A or B. And then from there, we've got to work out how many neutrons it's going to have. Well, we know that the mass number take away the atomic number gives us the number of neutrons. So that means it's going to be 31 when we do 57 take away 26. We've already disregarded C, so the only answer that has 2 correct values in is A. Another example that's going to use or make the most of the information provided to you on the periodic table. We want to know which of these has the smallest number of neutrons. I am going to go through and do the calculations for each one. I'm also going to put the data up so we can see once again, this is what you would be looking at on the periodic table. Now, to work out neutrons, as you know, we do mass number take away atomic number. So hydrogen, 3 take away 1 is 2. Helium, 4 take away 2 is 2. Helium 5 is going to be 5 take away 2, so that's 3. But lithium has got 3 protons, so if its mass number is 4, as this isotope is, that means it's only got 1 neutron. And so we have our answer. This is quite a common question, sometimes multi-choice, sometimes not, but we are trying to work out, first of all, what period, or what group, the element is in, and there's also information here that's going to help us determine which period it's in. First thing to look at is where there is a big jump in ionization energy, and we can see that that happens after 3 electrons. So 3 electrons are lost, then there is a big jump, and then it continues to increase. Now, the fact that it jumps after 3 electrons tells us that it's group 3, because that means that the 4th electron is being removed from a lower principal energy level. Now, that means that nitrogen and phosphorus can be dismissed because they are both in group 5, so we're with aluminium and boron. And after that, it's actually a really straightforward means of distinguishing between them, because boron only has 5 electrons, so it couldn't possibly lose 8. So we're now looking at which of the following atoms has 2 unpaired electrons in its ground or lowest energy state. Well, let's take a look at them drawn out, and we can see that helium has got 2 in a 1s sublevel actually, beryllium 1s2, 2s2, so they are both paired electrons. When we move on to nitrogen, that has got 3 unpaired electrons when you put those in. Oxygen has 2. So for that reason, the correct answer is D. So for this question, you need to have a good working knowledge of ionization energy and the trends, and also the reason for those trends, actually. Let's take a look at each of these. We want to know which requires less energy than the first ionization energy of oxygen. We can immediately dismiss B, because second ionization is always higher than first ionization. You're removing the electron from a positive ion, and you've also got a greater attraction on the fewer electrons by the same number of protons. For the rest of it, we can take a look at the graph that you will almost certainly be familiar with if you're revising this now. And we can see when we put this together that nitrogen and fluorine are either side of oxygen in the periodic table, but they're both higher. Oxygen has the dip. We don't actually learn about lithium across the neon, period 2. In the specification, we do sodium to argon, but the pattern is identical, and that is an application that you would be expected to be able to use to get to an answer like this. Now, sulfur, we're actually removing from a higher principal energy level. The electron's being removed from period 3 rather than period 2. So for that reason, the correct answer is A. So quite fiddly, let's take a look through what we have here. We've got 5 figures, and we've got magnesium, aluminium, silicon, phosphorus and sulfur. So it's going across the period in order of atomic number. Now again, if I put out my graph, and we can see the graph that goes there, we've got the general increase with a dip to aluminium and a dip to sulfur. And let's go through the answers and see what we can determine. Well, there are the 5. We can see that aluminium is lower than magnesium. There's an increase to silicon, an increase to phosphorus, but then a dip to sulfur. And let's compare that to the numbers that we have here. Well, A, we've got an increase from the first to the second value. So straight away, we know that cannot be the correct answer. On B, we have a dip, then we have an increase and a dip. So we do see that that follows the pattern exactly. So we can be fairly confident that that is the correct answer. We're going to double check on the remainder of them. Now C, definitely wrong because we've got that increase, but D does follow the pattern. It goes down, then it goes up, then it goes up, then it goes down. However, the drop is far too large. We know that the anomalies in the general trend, when we move to a higher energy P sublevel, or when we have spin-spin repulsion in a P sublevel where 2 electrons are being shared, that the dips are small. They certainly don't go down below any of the other elements than the one that precedes them directly. So D cannot be correct for that reason, so we can be confident that the answer is B.